Solid states. As we know from our chemistry, kwamba tuna various solid states. States of matter, in other words, kwamba tuna solids, tuna liquids na tuna gases. But as far as electronics is concerned, speaking of solid states, you generally mean the conductors, semiconductors and the insulators. Therefore, to start with the structure of an atom, to review kidogo yale ambayo tumeshasoma, an atom is the smallest particle which can take part in a chemical reaction. That's so basic, I hope you remember. It is made up of two components, the nucleus and the electrons. Within the nucleus there are protons and neutrons, we know that. So basically in the structure we are interested in the electrons as far as electronics is concerned. This is because we deal with electrons because it is the one that is excited from one energy level to another. It is the one that takes part in the reactions. It's the one that represents the properties of a certain metal. It is the one that carries all the properties of a given material. Therefore, this electron is a negative charged particle of an atom. It usually lies outside the nucleus, surrounding the nucleus in terms of orbitals or orbits. And the mass of the electron is approximately 9.1 times 10 power negative 31 kilograms. Electron moving around the nucleus possesses kinetic energy, potential energy. These are just basics. You see, just a revision. Total energy of electron is the summation of potential energy and kinetic energy at any point. So as far as our topic is concerned, we shall have the following important terminologies. We first have what we call valence electron. We know that the valence electron is the electron in the outermost orbit of an atom. That you have a nucleus, you have two shells. The atom, from our basic now knowledge of chemistry or level, because in advanced level we have different meanings. So the outermost electrons are what we call valence electrons. Covalent bond is the kind of bond which can be formed due sharing of electrons. These are basics. Energy bands, maybe this is important here, is the range of energies possessed by an electron in an atom. So an electron in an atom possesses different energies, so they can be classified into ranges from 1 to 2, maybe from 2 to 3, from 4 to 5. So those ranges are what we call energy bands. This term is important because it will be our next part that we're going to cover. We're actually going to cover about the energy bands. So there are types of energy bands. There are three types of energy bands. The first is the valence band, the conduction band, and forbidden gap. The arrangement of the bands in a solid state in a given material is in such a way that you always have conduction band which is of higher energy, forbidden gap or forbidden band that is usually intermediate between the valence band and the conduction band, and finally of the valence band, which is the lowermost level, because it's the energy level whereby electrons are usually normally at normal conditions at room temperature. So precisely, valence band is the range of energy possessed by valence electrons when they are not excited, when they are at rest. This band may be completely or partially filled with electrons. Again, you have conduction band. In this band, all electrons are free to move, so that electrons, when they enter or they attain energy of this level, they start conducting. That's why it is called conduction band. So when they attain these energies, they start conducting electricity. And again, we have forbidden gap, a gap or ranges of energy in which valence electrons have to cross for them to be excited to reach the conduction band so that they can conduct electricity. So it's the band of energy which separates between the conduction band and the valence band. Note, we have another terminology called the Fermi level. Fermi level, actually this is the energy level. Among those energy levels, there is a certain energy level where the probability of finding an electron is half. That there is a 50-50 probability to be occupied by an electron. So there are those such kind of, because there are ranges for a given material at given conditions, you can never expect to find an electron at that energy level. But there are certain energy levels in which the probability of finding an electron is usually 50%. You can either find it or you cannot find it by half chances. So such energy level is what we call the Fermi level. Sometimes it is called chemical potential or electron chemical potential. I'm telling you this because it is important. Sometimes they ask you to define these terms, so it's better get familiar with them. Again, the amount of energy in the Fermi level is what we call Fermi energy. It is used to determine the number of charge. You can use the Fermi level to determine the number of charge carrier available in a given band, used to classify different type of solid states. These are just notes, you can just get used to them. So as far as the topic is concerned, as I said, when speaking of solid state, we basically mean the three materials: the conductors, the insulators, and the semiconductors. What are conductors? We basically know conductors are any material that can conduct electricity. That at least is from the scratch, from the basic knowledge that we know. So all materials which can conduct electricity and whose valence band and conduction bands overlap, and more electrons lie in the conduction band. So for such cases we call that a conductor. Again, energy band description of a conductor, the arrangement of the energy bands. As I said here, that the conduction band and the valence band overlap. That's a typical feature of a conductor. That's why it is usually very easy for a conductor to conduct electricity, because the forbidden gap is usually a barrier that prevents electrons in the valence band to conduct electricity. So for electrons to conduct electricity, they have to cross the forbidden gap so that they reach the conduction band, so that they start conducting electricity. But for conductors, you can see the valence band and conduction band, they actually overlap, so that there is no any energy required. Only small amount of energy is required to excite some of the electrons from the valence band to enter the conduction band. As in the region of overlapping, already some of the valence band electrons are already in the conduction band. That's why it is very easy for a conductor to conduct electricity. In terms of energy band, valence band and conduction band overlap each other because forbidden gap is 0 in conductors. Hence, this overlapping is due to the absence of forbidden gap. So the effect of temperature on resistance and resistivity of conductor, we already covered this in the lesson number 3 concerning current electricity, that always for conductors, temperature is always direct proportional to the resistance. So temperature, the higher the temperature, the higher the resistance, because it disturbs the kinetic, the smooth motion of electrons, as you can recall in lesson 3. Again, since temperature is direct proportional to resistance, hence resistivity, so it must be inverse proportional to the conductivity, because conductivity and resistance are not proportionally related, they're inverse proportional. So temperature is inverse proportional to the conductivity of a conductor. For insulators, it's a bit different. These are materials which do not conduct electricity under normal conditions. So by the look of the eyes, kwa kuangalia tu energy band description, tumesema kwamba electrons in the valence band have to cross to go to the conduction band to conduct. So one among the reasons as to why insulators cannot conduct electricity, it is because the forbidden gap is very, very large, in such a way that it requires infinity amount, a very high energy to make valence electrons shift to enter the conduction band. So under normal conditions, this energy is usually not available to convert the valence electrons to jump all the way to the conduction band, because the forbidden gap is very, very large. So for insulators, the energy band description, as you can see here, it is around 15 electron volts. So there is a forbidden gap here, as you can see the arrangement. So electrons cannot be excited to the conduction, though they can, but under normal conditions the energy is very, very large. So under normal conditions it's usually not possible. Valence band is full of electrons, as you can see. The energy gap between the valence electrons and conduction band is very large, is very large. Therefore, to conduct is somehow difficult, about 15 electron volts. Therefore, very high electric field needed to push electrons to the conduction band, and therefore electrical conductivity is very small. Note, at room temperature, the valence electrons don't have enough energy to cross over the conduction band. When the temperature is raised, some of the valence electrons may acquire enough energy to cross over the conduction band. So it's an important hint that not that insulators cannot conduct electricity at all. No, it's when you have enough energy to make the electrons skip the forbidden gap, it's possible for an insulator to conduct electricity. However, under normal conditions, that energy is not achievable. Huwezi ukaipata. Semiconductors, which is our core focus here in this topic, these are materials whose ability to conduct lies intermediate between insulators and conductors. So you can imagine, kwa kufikiria tu haraka, you can imagine that the forbidden gap also is somewhere between a balance, is somehow balanced. It's less than an insulator, but it's not like a conductor, okay? That's why the conduction lies intermediate. Energy gap is about 1 electron volt. As you can see, for insulators it was 15 times more, but for here it's just 1 electron volt. So under some conditions you can conduct, under some conditions this might be large. So examples of semiconductors: silicon, germanium, and all group 4 elements, they are semiconductors except carbon. Carbon is a very good conductor, So as you can see, the description of energy levels, energy bands in the semiconductor is in such a way that the energy forbidden gap is small, about 1 electron volt. We have the conduction band and the valence band there. As you can see here, some of the electron semiconductors: germanium, indium, arsenic, silicon, zinc oxide, etc. In terms of energy bands description, the semiconductors have the following properties. They have a small energy gap compared to the insulators. Again, they are almost full of valence electrons, though some of the electrons are already in conduction band, so that it resembles more or less like the conductor. So almost empty of electrons on the conduction band, almost, but not completely. Therefore, semiconductors behaves in two ways, as an insulator and as conductor. So we shall see both cases, where it acts as an insulator and where it acts as a conductor. For the first case, the semiconductor is an insulator. At low temperature, the valence band is full while the conduction band is empty. It's because that the energy has been lowered by the lower temperature, so that energy required to excite the electrons becomes significantly high. Kwa hiyo, under low temperature, the semiconductor behaves as an insulator completely, unlike a conductor. A conductor under low temperature, the conductivity is very high. But for semiconductors, when they act as insulators, under low temperature, the conduction band is empty and the valence band is full, therefore it cannot conduct electricity. But on the other hand, condition gani ambazo zinaweza kufanya semiconductor hii ikact kama conductor? It is when it is at high temperature, such that the electrons can be excited enough to shift the valence electrons to enter the conduction electrons so that they can conduct electricity. So generally, for semiconductors, the resistance is inverse proportional to temperature, unlike the conductors. Okay, that under low resistance, high temperature. Okay, low temperature, high resistance. So they relate that way. As you can see the relation, sometimes they ask you to draw the relations. As you can see here, that resistivity or resistance with temperature is inverse proportional, while for conductivity and temperature is direct proportional. Again, we have properties of semiconductors. As you see, most electronic people, they prefer using semiconductors than conductors, for reasons that we shall see later. But for now, we can study the properties of semiconductors in which they have negative temperature coefficient of gradient of coefficient of resistance. This is because they are inverse proportional to the resistance. Therefore, they have negative temperature coefficient of resistance. Again, the electrical conduction lies between insulators and conductors. I have said earlier, semiconductors do not obey Ohm's law. As you can remember, ohmic conductors and ohmic non-ohmic conductors. You can recall the lesson 3, and you can see for yourself that semiconductors really do not obey Ohm's law. They are non-ohmic, but they are sensitive to light and temperature. Okay, they are sensitive to light and temperature. We shall see later. Again, we have types of semiconductors. We have two types of semiconductors. We have intrinsic semiconductors, which are pure semiconductors. Pure semiconductors, in which its electrical conductance is independent of additional impurities. That its conductance is entirely dependent on itself than on the external factors. As you can see, we have a structure of a pure semiconductor here. As you can see, this is a semiconductor of silicon. You view this diagram and you see for yourself that what we have here is only silicon. There is no any other material. So its conductivity mainly depends on silicon itself and not any other material. Silicon has a total number of 14 electrons in its atomic structure. Each atom of silicon can contribute to 4 valence electrons. You can see 1, 2, 3, 4. So that the atom is tetravalent. You can see it has 4 bonds around it. At low temperature, the valence electrons are tightly held by parent nucleuses of atoms. No free electrons on the conduction band. However, when thermal energy is applied, it breaks the covalent bonding and releases an electron, dislodged electron. The energy required to break this covalent bond is equal to the forbidden energy. So it is given that energy equal to the forbidden energy. Therefore, it crosses and enters the conduction band, and it can be delocalized, and therefore it can conduct electricity. Again, the second type, we have extrinsic semiconductors, which is impure semiconductor. This is impure semiconductor. It's the impure semiconductor which can be formed due to additional impurities or atoms on the pure semiconductor. So you find a pure semiconductor like this is added some of the atoms which are not of silicon, so that they can enhance or promote the conductivity of such semiconductors. Again, in the process of making extrinsic semiconductors, extrinsic semiconductors, so we have what we call doping, which is the increase or additional of control. This word controlled is very important, because otherwise if you don't control, you won't be doing any good to the semiconductor. Baada ya kuongeza conductivity, utakuwa unasababisha matatizo mengine. So is the increase or addition of control the amount of impurities to increase the electrical conductivity of a pure semiconductor. In doping, we use what we call dopants, which are the agents, the atoms that we are adding. So atoms which are added to the pure semiconductor is what we call dopants. So we basically have two types of doping. We have N-type doping and P-type doping. As their name suggests, N-types form a net negative charge, and P-type form transitional. Okay, we can just regard it a positive net charge, but later on we shall see it's not in such a proton. Though it is positive, doesn't mean it is a proton. So to start with, the N-type doping is obtained when pentavalent atom is added to pure semiconductor. Pentavalent electron. So this is the keyword here, that you want to create, because I said N-type doping, the net effect, as the name suggests, N, it should be negative. So it should be helping the semiconductor to attain more negative charges, so that it can assist and promote more conduction. So since you are having your semiconductors of group 4 having a valence of 4 electrons, inabidi unapokuja kufanya n-type doping uongeze atom yenye electron zaidi ya semiconductor yenyewe, ili hizo electrons zinazobaki ziwe ndo excess tumike kwenye conduction. Ndio maana tunapofanya n-type doping tunatumia pentavalent atoms. It means atoms ambazo ni za group 5. Okay? Yeah. So what we do, kwa mfano chukulia mfano ambapo tuna add arsenic. Arsenic ni compound ya group 5. So katika hii pure semiconductor tunatoa moja. Tunatoa atom moja. Suppose we remove hii ya katikati. Tunatoa hii hapa. Alafu tunachukua hii arsenic tunaweka hapa. Matokeo yake ndio itakuja kuwa kitu kama hiki hapa. Kwamba tumetoa silicon tumeka arsenic. Matokeo yake ni nini? Tumemtoa silicon ambaye alikuwa na bondi 4. Anakuja arsenic ana bondi 5. So 4 zitatumika kama zilivyokuwa zinatumika silicon kawaida kwa kila silicon ambaye anamzunguka, lakini moja itabaki ambao ndio hii itakuwa ni free excess electron. So kwa kufanya hivyo automatically tutaona tunakuwa tuna increase free electrons. So the more we replace the silicons, the more we are forming extra electrons. However, the word controlled is important. Otherwise, if you replace every silicon with arsenic, then hujafanya doping. Ulichofanya ni kuconvert a silicon semiconductor kwenda kuwa arsenic. Ndio maana kuna msisitizo wa point controlled amount of impurities. We have p-type doping. We have p-type doping in which, as the name suggests, its aim is to create a positive charge. But the most interesting thing here is that as far as these semiconductors are concerned, when we speak of positive charge, we don't speak of a proton. We don't speak of a proton. We have charge carriers called holes, in which the understanding of holes is somehow very complicated. However, a hole is just anywhere where an electron is lacking. So conventionally it is taken as if it is a positive charge, because you have removed the negative charge, you are leaving it more positive. So whenever there is one loss of electron, then it remains a hole where the electron was, and therefore that part is considered positive. Saying so inamaanisha ukitaka kufanya p-type doping lazima ulete atoms ambazo zina electrons pungufu, ili zile sehemu ambazo zilitakiwa kuwa na electrons zibaki holes, ambazo hizo holes ndio zitakuwa ni positive charge, ndio zitafanya p-type doping. Ndio maana tunasema kwamba p-type doping tunafanya kwa kutumia trivalent atoms, in which the atoms of group 3. Again, consider this silicon, but this time we replace this with aluminium, which is the group 3 element, the trivalent element. If we place with aluminium, we form something like this, that this time is aluminium here. But remember, silicon had 4 bonds, so aluminium can only offer 3. So therefore, it remains an empty space where an electron from another germanium, this time is germanium, silicon, they both have the same number of electrons, they have the same group. So automatically, this point where there was supposed to be an electron remains a hole. So the more you are adding trivalent, the more holes you're increasing, and the more you are making it more positive, and that's why we call it p-type doping. So you can ask yourself, maybe what is the importance of doping process? Doping actually increases the electrical conductivity of semiconductors. It increases the electrical conductivity of semiconductors. Why? Because it increases the number and type of charge carriers. For a conductor, the only charge carriers that are present are electrons, but for semiconductors, they are both holes and electrons. Automatically, the number of charge carriers have increased, and hence the conductivity will increase. Ukiweza kuichange semiconductor ikawa ukaimprove conductivity, huwa zinakuwa preferred zaidi kuliko conductors. It's because semiconductors are very easy to control, circuits and everything. They are very easy to control and manipulate. Therefore, from our knowledge of drift current, that you remember that drift current was given by I is equal to never. You remember N is the number of charge per unit volume, E is the electronic charge, V is the drift velocity, and A is the cross-sectional area of a conductor. But for this time, if you want to get the total number of, the total current, you should take the number of electrons and the number of the holes. Okay, the number of electrons and the number of holes. That's why we say for here electrical conductivity has increased because of the inclusion of the charge conduction. Important distinctions to note. You can read here. We have differences between N-type and P-type. We have differences between metals and semiconductors, and we have differences between intrinsic and extrinsic semiconductors. You can just read here. They are very simple things. You can read for yourselves there. Again, we have disadvantages of semiconductor devices, that they're extremely heat sensitive. They're very, very sensitive to heat. Okay. Ndio maana transistors amplifier yanakuwa na ungua mara nyingi, because they are sensitive to heat. Na kukitokea tatizo lolote la overheating tu, kifaa kinaharibika. Again, can only handle small currents and low inverse voltages. As you can see, the radios, the amplifiers, they handle small currents. You cannot put very, very large currents from far in the radio, you will destroy it. So they usually work best when handling small currents and low inverse voltages. Otherwise, they usually don't allow inverse voltages. Again, they can't stand an overload even for a short period. Whenever there is an overload, might cause breakdown, melting, or whatever effect that can occur. So they don't stand on overload. They usually require specific amount as per its rating. Kwa ukizidisha tu amount ya umeme ambao unaingiza kwenye kifaa cha semiconductor, unakidestroy, because hakiwezi kuaccept overload for a long time. Advantages, however, of semiconductors is that they are smaller and have longer life. They are simple and cheaper, require no filament power. So these are just notes, you can pass them through for yourselves.